Hello, dear listener. Settle in softly, perhaps closing your eyes, or gazing at a peaceful point in the room. Allow your breath to deepen, slowing gently, as we prepare to drift back through time, not just to recount events, but to truly feel the currents of human thought, the quiet triumphs, and the profound mysteries that have shaped our understanding of the universe. Tonight, we embark on a journey into the very fabric of reality, into the history of quantum mechanics. This isn't merely a chronicle of dates and names, but a tender exploration of how our minds, in their infinite curiosity, began to unravel the most intricate secrets of existence, secrets that lie beneath the surface of what we perceive as solid and continuous. The history of quantum mechanics is, in essence, a fundamental part of the much larger, sweeping story of modern physics itself. It's a tale that speaks to the deepest questions we can ask. What is matter? What is energy? What is reality, truly, at its most fundamental level? Our journey begins in an era often referred to as the old, or older, quantum theories. Imagine a time when brilliant minds, peering at phenomena that defied classical explanation, began to conceive of entirely new ways of seeing the world. These were the first whispers of a revolution, emerging as scientists grappled with seemingly disparate puzzles. There was the enigmatic glow of black-body radiation, where objects heated to incandescence emitted light in patterns that classical physics simply could not predict. Then, the peculiar dance of the photoelectric effect, where light, when shone upon certain metals, would cause electrons to be ejected, but only if the light possessed a certain minimum energy, regardless of its intensity. And finally, the beautiful, yet perplexing, solar emission spectra, the distinct lines of color emitted by excited atoms, like a celestial fingerprint, which held a secret about how energy was stored and released within them. These individual phenomena, like scattered pieces of a profound mosaic, began to hint that something was fundamentally different in the microscopic world than in the macroscopic world we inhabit. Building upon the robust, yet ultimately incomplete, framework of classical mechanics, the grand edifice constructed by giants like Newton, a new era dawned. It was around the year 1925 that the invention of wave mechanics by the brilliant Erwin Schrödinger, and its subsequent expansion by many other pioneering minds, truly ushered in what we now call the modern era of quantum theory. Imagine the excitement, the intellectual ferment, as these new ideas began to take root and blossom, providing answers where none had existed before. The story didn't end there, of course. The human quest for understanding is a continuous unfolding. Paul Dirac, with his extraordinary insight, wove together quantum theory with Einstein's theory of relativity, leading him to explore quantum theories of radiation. This profound work culminated in the creation of quantum electrodynamics, or QED, the very first quantum field theory. This was a monumental leap, allowing us to describe the interactions between light and matter with astonishing precision, revealing an even deeper layer of reality where particles are not just tiny balls, but excitations in pervasive quantum fields. And as the tapestry of quantum mechanics continued to unfurl, its threads began to intertwine with other branches of science. The history of quantum chemistry, for instance, which forms the very theoretical basis of chemical structure, reactivity, and bonding, is deeply interwoven with these events. It's a testament to the universality of these new ideas, showing how they provided the foundational language for understanding how atoms bond to form molecules, how reactions occur, and ultimately, how life itself functions at its most basic chemical level. It was amidst this vibrant intellectual landscape, in the early 1920s, that a group of visionary physicists at the University of Göttingen, including the towering figures of Max Born, Werner Heisenberg, and Wolfgang Pauli, sought to name this nascent, revolutionary framework. They coined the phrase, in German, Quantenmechanik. The term itself first appeared in print in September of 1925 in a paper by Bourne and P. Jordan titled Zur Quantenmechanik, on quantum mechanics. Imagine the gravity of that moment, giving a name to something so profoundly new, something that would forever alter our perception of the universe. Let's gently unpack that name, quantum mechanics, and let its meaning resonate with you. The word quantum itself descends from the Latin word meaning how much. And indeed, it speaks to a profound revelation that certain properties in the universe are not continuous, but discrete. Something that is quantized, much like the energy of Max Planck's harmonic oscillators, can only take on specific, distinct values. Think of it like a staircase, where you can only stand on individual steps, not anywhere in between. Or, as the text beautifully illustrates, consider money in most countries. It's effectively quantized. You can have a certain number of dollars and cents, but you can't have half a cent. The lowest value coin in circulation acts as the fundamental quantum of money. In the quantum world, energy, angular momentum, and other fundamental properties behave in this surprising, stepped manner. This was a radical departure from the classical view, which largely assumed a smooth, continuous spectrum of possibilities. And mechanics? That's the branch of science that traditionally deals with the action of forces on objects, predicting their motion and behavior. So, when we combine these two words, quantum mechanics describes the part of mechanics, the study of motion and forces, that deals with objects whose particular properties are, in fact, quantized. It's the mechanics of the discrete, the stepped, the fundamental building blocks of reality. As we lull ourselves deeper into this historical narrative, let us consider the profound backdrop against which quantum mechanics emerged, the triumph and the trouble at the very end of the classical era. The 19th century was a period of immense scientific achievement. Grand theories had been constructed, explaining a vast array of phenomena with elegant mathematical precision. Yet, like faint dissonances in an otherwise harmonious symphony, there were discoveries, both great successes that seemed to push the boundaries of understanding, and puzzling failures that hinted at something deeper, which collectively set the stage for the emergence of quantum mechanics. The classical worldview, while magnificent in its scope, was starting to show its limitations, like cracks appearing in a grand, ancient edifice. Let's gently explore one of the most enduring debates that preceded this revolution, the wave theory of light. For centuries, the nature of light had been a profound mystery. Beginning around 1670 and extending over 3 decades, the monumental figure of Isaac Newton, with his unparalleled genius, developed and championed his corpuscular theory. He argued, with compelling logic, that light was composed of tiny particles, or corpuscles. His reasoning was powerful. The perfectly straight lines in which light seemed to travel, as observed in reflection, strongly suggested a particle nature. After all, at that time, no wave theory could adequately demonstrate light traveling in such precise, straight paths. He even explained refraction, the bending of light as it passes from one medium to another, by positing that these light particles somehow accelerated laterally upon entering a denser medium. It was a complete, coherent theory, grounded in the observable phenomena of his time. Yet, around this very same period, and in the centuries that followed, other brilliant minds were pursuing a different intuition. Contemporaries of Newton, like Robert Hooke and Christian Huygens, and much later, Augustin Jean Fresnel, mathematically refined the wave viewpoint of light. They proposed that if light traveled at different speeds in different media, then refraction could be elegantly explained as the medium-dependent propagation of waves. Imagine waves gently shifting direction as they encounter a change in their environment. This vision crystallized into the Huygens-Fresnel principle, a remarkably successful framework for reproducing light's complex behavior. The truly decisive evidence came with Thomas Young's groundbreaking double-slit experiment in 1801. Imagine light passing through two tiny, closely spaced slits. If light were purely particles, you would expect to see two bright lines on a screen behind the slits. But Young observed something entirely different, a pattern of alternating bright and dark fringes, an interference pattern, precisely what you would expect from waves. This discovery was a profound revelation, seemingly confirming the wave nature of light. The image of waves interfering, canceling each other out in some places, and reinforcing in others, was undeniable. Still, the wave view did not immediately or entirely displace the ray and particle view. Old ideas die hard, especially when supported by the authority of Newton. However, as the 19th century progressed, the wave theory began to dominate scientific thinking about light. The crucial reason for this growing acceptance was its ability to explain phenomena that the alternatives simply could not, such as polarization. Imagine light waves oscillating in specific directions. This polarization was readily explained by wave theory but remained a profound puzzle for particle theories. Then came the grand synthesis, a breathtaking moment in physics, with James Clerk Maxwell. He found that he could take his previously discovered equations, which described the behavior of electric and magnetic fields, and with only a slight, elegant modification, apply them to describe self-propagating waves of oscillating electric and magnetic fields. It quickly became apparent that visible light, the spectrum of colors our eyes perceive, along with the invisible realms of ultraviolet light and infrared light, were all fundamentally the same thing, electromagnetic waves of differing frequencies. This monumental unification of electricity, magnetism, and light into a single, elegant theory became a critical ingredient, a foundational piece, in the very beginning of quantum mechanics. It was the crowning glory of classical physics' understanding of light, making the subsequent quantum revelations all the more startling. Moving from the nature of light to the nature of matter, we arrive at the emerging atomic theory. During the early 19th century, diligent chemical research by figures like John Dalton and Amadeo Avogadro lent increasing weight to the ancient idea of the atomic theory of matter. This was the proposition that all matter is composed of tiny, indivisible particles called atoms. Building upon this, giants like James Clerk Maxwell and Ludwig Boltzmann, along with others, constructed the kinetic theory of gases. This theory elegantly explained the macroscopic properties of gases, their pressure, temperature, and volume, as arising from the statistical average behavior of countless individual atoms or molecules in constant, random motion. The successes of kinetic theory were impressive, providing powerful credence to the idea that matter truly is composed of atoms, even though these atoms were far too small to be directly observed. Yet, even in its triumphs, the kinetic theory had its shortcomings, subtle inconsistencies and unexplained phenomena that would only find their ultimate resolution with the development of quantum mechanics. It's fascinating to note that even then, the existence of atoms was not universally accepted among physicists or chemists. For instance, the renowned philosopher and physicist Ernst Mach was a stout anti-atomist, believing that science should only deal with directly observable phenomena, not hypothetical entities like atoms. This resistance highlights the intellectual courage it took to embrace these new, often counterintuitive ideas. The earliest, most subtle hints of problems within the robust framework of classical mechanics began to surface in relation to the temperature dependence of the properties of gases. These were the first, quiet whispers that something deeper was at play. And then, a truly prescient insight emerged from Ludwig Boltzmann in 1877. He suggested, with remarkable foresight, that the energy levels of a physical system, such as a molecule, might not be continuous, meaning they couldn't take on just any value, but could, in fact, be discrete. Imagine, again, those steps on a staircase for energy. Boltzmann's rationale for the presence of these discrete energy levels, particularly in molecules like those of iodine gas, had its origins in his sophisticated statistical thermodynamics and statistical mechanics theories. His ideas were backed up by rigorous mathematical arguments. This early, profound intuition about discreteness, though not fully elaborated as a quantum theory at the time, was a significant intellectual precursor. It's a powerful reminder that sometimes, the seeds of revolutionary ideas are planted decades before they fully blossom, awaiting the right conditions and the right minds to nurture them into a complete paradigm shift. This quiet suggestion by Boltzmann, nearly 20 years before Max Planck would put forth the first fully articulated quantum theory, underscores the long, winding path of scientific discovery, where insights slowly accumulate, building towards an inevitable breakthrough. And then, as the 19th century drew to a close, a pivotal discovery occurred in the final days of the 1800s. J. Thomson, through his ingenious experiments, definitively established the existence of the electron. He showed that these tiny particles carried a negative charge, precisely opposite but equal in magnitude to that of a hydrogen ion, and startlingly, had a mass over 1,000 times less than that of the lightest atom. Imagine the profound implications. The atom, once thought to be the indivisible building block of matter, was itself composed of smaller constituents. The universe was far more intricate, far more layered, than anyone had previously imagined. The discovery of the electron was not merely finding a new particle. It was cracking open the atom itself, revealing an inner world of profound complexity, and initiating a new era of physics where the very notion of fundamental would be constantly redefined. We've only just begun to scratch the surface of this incredible journey, moving from the grand classical worldview to the first inklings of a universe built on the discrete, the quantized. As you continue to breathe softly, let these ideas gently settle within you. Feel the vastness of the intellectual landscape we've traversed, the sheer wonder of human curiosity, and the patient unfolding of understanding that slowly, inexorably, led us to the quantum realm. The path ahead is filled with even more astonishing revelations, but for now, rest in the quiet contemplation of these beginnings. Good night, dear listener, and may your dreams be filled with the gentle hum of discovery.